Good morning, everyone, and thank you for the kind introduction through our session share. I am deeply honored to be able to present to you today the results of our study, a comparative evaluation on the quality of manual and automatic test case generation techniques for scientific software. In this case, we did a case study of a Python project for material science workflows. Now, since I assume that most of us here today are all software engineers, let me give you a very, very brief introduction into material science. So what is the basic idea? Assume for a second that you are a material scientist and you have a brilliant idea for some type of material that might revolutionize batteries or photovoltaics, for instance. So you could obviously synthesize the entire material and try out in the wet lab every single material property. Now, that of course will always take a lot of money and a lot of time. So computational material science was born, where the computational material scientist takes their idea, puts it into some format, pushes that input into a massively complex simulation code called DFT code, density functional theory. And after a couple of weeks or months even, some type of result will fall out of that entire computation. Then you come back to that result and look at it for a while, and you might find, my material idea didn't work, my geometry is all wrong, or maybe the material in its generality didn't actually work. So you go back to the simulation and simulate some more. After a couple of these iterations, you might find a material that is somewhat interesting in the base case. So you take that material and take a couple of new parameters and put it back into the massive simulation to then find out some more of the more advanced material properties. Now, these simulations, they are a human in the loop system. They are quite resource intensive and they are monolithic. They are monolithic because we can't analytically solve the quantum physics that are used within this simulation. So we have to employ numerical approximations. However, this is only half the story. Unfortunately, this massive thing that we have seen in this slide here is just one of very, very many of these potential simulation codes. So to make sure that other scientists can actually work with the data that we create and that our simulations produce, we have to run our data through some scripts and fit it to a unique and or maybe even universal type of file. So what are we looking at in our study? We are looking at the atomic simulation environment, or ASE. So the software under test is a Python wrapper that is wrapping all of these codes that we have seen here, where we can build, manipulate, and basically do every single thing to these atomic systems that we have in our mind to simulate. We can create and generate input files for these different DFT codes. So maybe you want to use the exciting code, or maybe you want to use the VASP code. The ASE environment is able to generate input files for those different DFT codes. It is then also able to call the executables of those DFT codes, and it is able to collect and somewhat analyze the results that these DFT codes will give you. So now that we know where we are heading, let us actually talk about what we were asking ourselves. How can we use these automatically generated test suites of our test case generation algorithms and how do they compare against each other, and against a manually created test suite as well. We have a couple of experimental results. Do not be alarmed. The next table is going to be a bit big. We're going to go through it step by step. Let's start at the very left. We are looking at both branch coverage and mutation coverage for the baseline, so the initial testing suite that came with the tool ASE. In our case, we see that the baseline only reached about a quarter of the branches and had a somewhat bad mutation coverage, so somewhat bad sensitivity of only 3%. We then created a manual test case in about 8 hours of work by a single person, our first author, Daniel Trübenbach. He then found a test suite that covered with 31 test cases the entirety of all branches, and was also quite sensitive against introduced fresh bugs, shown here through the mutation coverage of 0.9. For the 4 looked at state-of-the-art automated test case generation algorithms, we will now look at these information presented here in form of a box and whisker plot. Now, let us start with the branch coverage. We see that MIO actually fared the best in all of our runs. So we ran each of the algorithms for 600 seconds, and we ran it 30 different times to see how randomness actually fared here. We also see that both dynamosa and whole suite generation are quite close to each other, and as expected, they all fared a lot better than the FD random feedback directed random approach that is somewhat similar to the Java rendupe approach. Now, take a look at the branch coverage on our left axis here. We only see somewhere around 60% is the absolute maximum. Keep in mind, we had in our manual test suite a branch coverage of 100%. So there's a massive difference already. If we now take a look at the mutation coverage as well, we see how little the automated test case generation approaches were able to actually create sensitive test suites. This is unfortunate, and we also noted that for some reason that we couldn't explain, the whole suite fared even worse than the FD random approach. Now, the search-based software testing community and this particular workshop, we aim at actually improving our test case generation algorithms, and we actually want to see what might be hindrances to the actual use in the wild for our systems. Well, let us come to our conclusions and observations already. What did we see? In our study, we found that while all of the approaches managed to provide an improvement over the baseline in all cases, we also noted it was significantly worse than the manual test suite. And the manual test suite, creating that in 8 hours of work, didn't actually take too long for a system that was rather complex. So what might be the pitfalls in practical use? So pitfall number 1 that we identified is that our current algorithms cannot work with complex and structured inputs such as material data science input data. Pitfall number 2, the dynamic typing of Python might actually interfere with the generation power of our approaches, we will actually have to see whether we can't use specific and new approaches for languages that employ this dynamic typing, such as Python. And number three, when we try to explain the automatically generated test cases to our domain scientists, it was quite problematic for us to do so because of the naming scheme employed by most of the test case generation algorithms. I hope this has put a bit of a light onto the pitfalls that we discovered during our study. And I would hope that this might spark a new discussion about how to solve all of these things. It has been my great pleasure to present to you today our case study on the material science data. And if there are any questions, I am happy to answer them now in the discussion.